conservation of energy. In this case, actually, you know what? Before we do a problem, I want to just like lock down what conservation of energy is. Just as a reminder, the law of conservation of energy has this idea that energy can't be created or destroyed. In a closed system. Well, it really can't be created or destroyed in any system, but it can't be created or destroyed in a closed system either. And what that means for us is that the total energy of a system before something happens and the total energy of that system after, after something happens is going to be the same. The total energy before and after will be the same. So I got this slingshot, and this slingshot is shooting a pebble up in the air. And if you don't know what a pebble is, look, there's a little vocabulary note. A pebble is a small rock, okay? So we got this slingshot that's shooting a pebble up into the air. And the information that we've got here is that this pebble has a mass of 20 grams. And the nice thing about metric conversion is that we just move the decimal place over a few times. And every time in physics we do a calculation, we have to have it in kilograms, okay? So kilograms is our SI unit of choice for physics. So 0.0200 kilograms, because there's 1,000 grams in a kilogram. So we move that decimal place over 3 times. Okay? And you don't have to show your work on that. We could do that as head work. Okay? Now another thing that we could say is that as this pebble is being shot up into the air, it's experiencing gravity, acceleration due to gravity, 9.81 meters per second squared. We won't worry about it being down, because as we've said before, we don't have to deal with reference frames with energy, right? It's just a magnitude thing. But I do have this pebble, this little rock. It's been shot up, and at the moment that we're talking about right now, it's 4 meters above the ground. So I want to say that that spot, that location, is, see where this rock is right now? Height A. I want to say that that's my 4 meters. And here, in this particular situation, the diagram has been provided to us. But there's all this information that's coming at us. The reason I've got this diagram pre-drawn this time is to highlight the importance of having like a multiple snapshot diagram. You know, the rock is at position A, it gets up to position B. Maybe we could talk about what was happening when it was at position C. Having these multiple snapshots is helpful for us to like keep track of all of the givens, okay? And for you, you're not going to draw something this complicated. You can just draw circles and label them A, B, C, right? Like it can just be very, very simple, very stick person kind of drawing. But we keep on reading and it says it's traveling at 3.20 meters per second. Okay, so at position A, its speed is 3.20 meters per second. Happens to be up, but remember with energy we're not worried about reference frames. So I'm just saying that that's the speed that it's going at.
Is that 3.2?
That's 3.20 meters per second. I'm just taking that straight off of the givens right here in this story. The first question is, what's the total mechanical energy of the pebble at the moment described above? Now the way we're defining mechanical energy, this is total mechanical energy at position A. The way that we're going to define mechanical energy is we're only going to include gravitational potential energy and translational kinetic energy. I know that there's chemical potential and elastic potential and rotational energy and vibrational energy, but for the purposes of grade 11, we're going to only consider gravitational potential and kinetic energy as our mechanical energy. This is like a nice simplification for us. Believe me, this is good. This is a good thing to start with, okay? So we say total mechanical energy for us, we know gravitational potential energy was mass times acceleration due to gravity times height. Now it's gravitational potential energy at position A, so I'll say that it's height A, plus the kinetic energy, we expand that out as 1/2 m times VA squared, so the speed at position A squared. And we say, okay, well, the total mechanical energy, it looks like I have all the pieces of this puzzle. I know the mass, I know the acceleration due to gravity, I know height A. Again, I know the mass, and I know how fast it was going at position A. I've got all the pieces. We can just plug things in here. So we've got 0.02 kilograms times 9.81 meters per second squared. And people with calculators, you're going to help me out on this one. Times height A, 4.00 meters plus 1/2 times 0.02 kilograms times, what was it? VA was 3.20 meters per second. Don't forget to square that speed. Most common mistake with this particular calculation, square that speed at the end. And just to make sure we get that good lucky feeling, there are a couple of 8s in the answer. You'll know that you have it when you have a couple of 8s in the answer. Yes, sir?
Why is the speed squared?
Why is the speed being squared? Because it's a part of the kinetic energy
Oh,
formula.
I didn't see that.
Yeah, so the EK in general is 1/2 mv squared. So in this case, it's VA squared, but we got to square that V. Yeah,
0.8872.
nice. 0.8872 joules. And how many people recognize that there were only 3 sig figs in any of the givens, right? Yeah, so I'm being friendly about this. Nice rounding, approximately 0.887, oopsie, 7 joules. And we could have a little therefore statement. We could say therefore, the total mechanical energy of the system is, and we're just putting it back in context, 0.887 joules. Fair enough. But then the follow-up question, what's the maximum height that the pebble can reach? And we've done enough of these kinds of questions when it was kinematics. And so we can't just like say the kinematics unit is over, we got to forget about it. That's not the way physics works. Everything gets dragged forward. And I'm not even sure that dragging everything forward is the great way to think about it. I was talking with somebody about this yesterday, and it's not really like a linear time thing, like we're dragging things forward in a storyline. The conversation went like this: isn't it more like we're building a foundation? And if you build a house, if you build a foundation, the rest of the house sits on that foundation, right? And so here we are, like dynamics unit was maybe like the first floor. We're building the second story of the house, but we're still resting on the foundation that we started with, which is kinematics, right? So we can't just throw out the foundation. We got to still like look back to the foundation to make sure that we're still steady about things. And as I look back to the foundation, if I shoot something straight up in the air, vertically, what's its speed when it gets to its highest height? 0, yeah. Kinematics tells us that. So I'm just going to make a little note about that. I'm going to say that VB, based on the foundational knowledge I know from kinematics, is equal to 0 meters per second. So when somebody asks me the question, what's the maximum height that the pebble reaches, that's something that I know. I know that E total A, because of conservation of energy, is going to be equal to E total B. And I could expand out both sides of that. I could say E total A would be equal to EKA plus EGA. We said that already in the first question. E total B would be equal to EK at position B plus EG at position B. But what you folks just told me was that at the top, it's going to come instantaneously to a stop, right? What does that let me zero out right now? Yeah? No, not EGA. The fact that it comes to a stop at the top. Yeah. No, EGB isn't 0 at the top. EKB. Yeah, and actually, you know what? Maybe I'll write it an extra line to make sure it's really obvious why it's EKB, okay? So 1/2 mVA squared plus mass times acceleration due to gravity times height A equals 1/2 mvB squared plus mass times acceleration due to gravity times height B. When it gets up to the very, very top, what we just said was that VB was equal to 0, right? So that means that if this VB is equal to 0, that means that that whole term zeroes out. EKB zeroes out. So I'll just backtrack and call that 0. Notice that the height is not 0 at position B. I definitely can't say that. In fact, I'm trying to find height B. That's the thing I'm looking for. Now, as it turns out this time, haven't I already figured out EKA plus EGA? And that's what I did in part A, right? So I feel like I'm not going to do that again. I'm just going to write it out. 0.8872 joules. That's what 1/2 mVA squared plus mass times acceleration due to gravity times height A is. I already did that math. I'm not going to do that again. But I know that that's equal to mass times acceleration due to gravity times height B. And if the goal is to find the maximum height, that height, B, I'm going to get HB all by itself. So 0.8872, the unrounded value, in joules divided by mass times acceleration due to gravity is going to be equal to height b. So I'm just getting hb all by itself there. So hb, I can sub in my values, 0.8872 joules divided by a mass of 0.02 kilograms times 9.81 meters per second squared. Somebody help me out. What do you get?
45.2191.
So close. I feel like we got a decimal place error. Yeah?
4.52191.
Yeah, 4.5219. I feel like maybe.
I put in 0.002.
Oh, that's it. Yeah. Yep. So 0.02 grams. It's important to get our unit conversions right on that. But we get 4.5219 meters. Do we have some broad agreement on this one? Okay, good. All right, so remember we've got to round this off to three significant figures. So it looks like it's going to round off to 4.52 meters approximately. And of course we can say therefore the maximum height is. Now, there are going to be people that say, well, wait a minute. Did you really have to use conservation of energy to do this problem? Remember I said once before, we started this house building project with a foundation. Somebody could say, going back to my foundational knowledge, V2 squared equals V1 squared plus 2A delta D. Can you guys see that I could have used a kinematics approach to do this thing? 100%! Yes! Now, if you're on a test asked to solve this using conservation of energy laws, you'd have to do it the way we just did it. If it was the exam and it just says, find the maximum height that it goes to, do it any way you want. The point is that, yeah, they're consistent with one another, they work together, and what's more is by bringing in this idea of conservation of energy, we're actually bringing another perspective to how we think about things, okay? So it's not just kinematics, it's not just the basics of motion, it's about the idea that energy is conserved, okay? So yes, we can use the old, but yes, we can also use the new, and I feel like embracing the new sometimes expands our minds just a little bit, okay? So that's all I'm saying about that one. Let's take a look at this next question. It says, how fast was, notice, how fast, that's speed. How fast was the pebble going when it was launched? So what we're looking for here, look at my diagram. It looks like we're trying to find VC. We're trying to find that initial launch speed. Now, at VC, based on the way that we got our diagram done here, it looks like HC is equal to what value? Yeah, 0. So the way we've defined our heights, all those heights are being measured relative to HC being 0, right? We've figured out HB now. I guess we could throw that in there, something we just figured out. It's about 4.52 meters. Not that we're going to use it again in our calculations, but we could label it up anyway if we wanted to. But it says, how fast was the pebble going when it was launched? All right, so I want to start out with this idea of conservation of energy one more time. E total A equals E total C. If conservation of energy is a thing, they should be equal to each other. And again, I've already calculated E total A, but E total C would expand out as EGC plus EKC. And just to make sure we don't have the same confusion as we had before, I want to expand EGC out, MAG HC, plus 1/2, we'll expand EKC as well, 1/2 MVC squared. Is there anything here that I can zero out? Yep. Yeah. Why? Yeah, so we can zero this guy out because she says the height's 0. So that one's 0, which means the whole term is 0. Nailed it. That means that E total A is equal to 1/2 MVA, C squared. Remember, we're trying to find that initial launch speed. So we can take the 2 over to the other side if you like. 2 times E total A equals MVC squared. Now I'm going to write out every step because I had a few people saying that they're having a hard time following the math, so I'm going to break it down. Then I would divide both sides by M. Notice that the mass cancels out on that side. Give myself a little thought flow. So now I've got VC squared is equal to 2 times E total A divided by mass. My next operation would be to square root both sides. And then I'm ready to plug things in. So I can say VC is equal to 2 times E total A. And E total A, we said earlier, unrounded, was 0.8872 joules divided by the mass, which we said was 0.02 kilograms, all rooted. I'll give you a good lucky feeling here. It should start with a 9 if you've got it. Yeah?
9.4191.
9.1?
Yeah.
Is it 9.1?
Yeah.
All right. Meters per second. And of course, we're going to round it off to 3 sig figs anyway. So 9.42 meters per second. Now somebody's going to say, is it up or is it down? Well, based on the scenario, we know that it's up. We don't have a reference frame way of talking about this because, let's face it, whenever you square root something, you're going to get plus or minus. That's a mathematical artifact, that's fine. But if you wanted to talk about the velocity of this thing and give it a direction, we would have to go back and use our human brains to figure out what direction was this thing going in. Well, it was launched upward. It wasn't launched downward, right? So we could say that it's up, but that's not what we were asked anyway. We were asked about the speed, which is just how fast, okay? And of course, we could say, therefore, the pebble was launched at 9.42 meters per second. And again, there's going to be people that say, well, couldn't we figure that out using kinematics? And to that, I would say, what do you think? Yes, of course we could. But we're providing a new perspective, an energy perspective. That's all. It's a deeper perspective. We're adding more onto our knowledge.